Okay, let's get into this. For decades, the entire engine of modern tech has been Moore's law, right? Engineers just keep shrinking transistors.
Right.
But now, as we're pushing below that 10 nanometer barrier, we are hitting some pretty fundamental physical walls. The manufacturing itself is so complex that the design stage, it's just grinding to a halt
It is. It's a genuine computational crisis.
just to build the next chip.
What's so fascinating to me here is how a physical crisis, the
Yeah.
difficulty of just etching these tiny shapes, it created a parallel crisis in algorithms.
How so?
Well, the old computational tools, they just weren't built for this level of insane complexity. They turned a problem that should be solvable into this tangled mess.
So our mission today is to do a deep dive into a framework that, well, it completely threw that out. It replaced a slow brute force method with a really elegant network flow solution.
And elegant is the right word.
And when we say elegant, we also mean incredibly effective.
Mm.
The paper we're looking at, a 200x leap in chip layout, solving cut conflicts with network flow. It details a huge engineering breakthrough.
Mm.
They didn't just find a faster computer. They found a fundamentally better way to think about the problem. And that gave them a 200x speed up.
In a step that used to bottleneck the entire design pipeline, this is the stuff that unlocks the future.
To really get the scope of this, we have to start at the physical level, on the factory floor. Why are the old ways of making chips breaking down?
Okay, so imagine you're trying to draw a microscopic circuit diagram on a silicon wafer. When the features were bigger, say 20 nanometers, you could still use standard lithography.
Kind of like a stencil.
Pretty much. But below 10 nanometers, the traditional 2D layouts just, they explode in complexity. You simply cannot print those intricate, complex shapes reliably anymore.
I remember reading about things like self-aligned multiple patterning or ANT-MP. It sounded like a total nightmare.
Oh, it was, and it still is. SMP requires multiple masks, multiple alignment steps just to create one tiny feature. It multiplies the chances for error, for defects, and adds huge cost.
So the industry had to simplify.
They had to standardize the pattern, and that led to this new standard called the 1D end cutting layout design.
So tell us about that. How does that simplify the actual printing?
It makes the initial pattern totally uniform. Instead of trying to etch all these complex squiggly lines,
Right.
you first just print a grid of perfectly parallel unidirectional lines across the whole chip, like tiny uniform rail tracks.
Okay, so you have a grid of lines. Then what?
Then you come in with a second, much simpler cut mask. And this mask's only job is to make perpendicular cuts.
So it just goes in and snips the lines it doesn't want?
Exactly. It trims away the segments you don't need. What's left over are your actual functional target wires, the ones carrying the signal, and everything else just becomes a dummy wire.
Which acts as insulation or just a placeholder?
Yep. It dramatically simplifies the manufacturing.
But of course, every solution creates a new problem. And in this case, the paper calls it the new manufacturing bottleneck. Cut spacing conflicts.
Precisely. Because if two of those tiny cuts are too close to each other, if they violate that minimum distance, they call it Dumin, the lithography process can't tell them apart.
They just blur together.
They blur together or they fail to etch at all. And that part of the chip is just dead. It's unmanufacturable.
So the job becomes eliminating all those violations. And the standard fix for that is called cut redistribution.
That's it. You find the cuts that are too close and you basically slide them horizontally within their little allowed gap until they're far enough apart.
Or just till they line up perfectly.
Exactly. So they can be merged into a single cut, a single shot in the lithography process.
But this brings us to the core trade-off here. When you slide a cut to fix a conflict, you're not just moving the cut, you're actually stretching the wire segment next to it.
These little stretches are called wire extensions, and they're unavoidable in this process.
And why are wire extensions a bad thing?
Parasitic capacitance.
Ah,
You can just think of it as signal drag. The longer the wire, even by a few nanometers, the more energy leaks out and the slower the signal travels through it.
So if you stretch too many wires, even if the chip is perfectly manufacturable,
It's too slow to sell. It fails to meet its designed clock speed.
so engineers are completely stuck. They have to eliminate all the physical conflicts to even make the chip.
But they have to minimize the total wire extension to make sure the chip is actually fast enough to be useful. It's a perfect and perfectly horrible optimization problem.
Okay, so that's the setup. A massive, complex puzzle. Thousands of tiny cuts, hundreds of thousands of rules, all while trying to keep the total wire length down. So
Yeah.
how did computers handle this before the big breakthrough?
The standard workhorse for problems like this was a technique called integer linear programming, or ILP.
ILP.
Yeah, and conceptually, ILP is incredibly powerful. It treats the exact physical exposition of every single cut on the chip as a variable it needs to solve for.
And then you just encode all the rules of physics, the minimum spacing, the timing limits, as this giant set of mathematical inequalities.
That's it. And the solver's job is to search for the one perfect set of coordinates that satisfies every single rule while minimizing that wire extension cost. But, and this is the big but,
There's a catch.
there's a crippling flaw. ILP is, in computer science terms, NP hard.
NP hard. Okay, that's one of those terms that sounds very serious. What does that actually mean for the engineer trying to design a chip?
It means that as you add more cuts to your design, the time it takes to find the perfect solution doesn't just grow, it explodes exponentially.
Right.
For a small layout, it's fine. The solver can check every combination pretty quickly. But for a modern chip with tens of thousands of cuts, the search space becomes astronomical. You're basically asking the computer to search a giant maze blindfolded.
So we're not talking about a few minutes of compute time.
No, we're talking hours or even days. We can put a hard number on it, actually. The paper mentions a benchmark on a production level layout, about 8,000 lines.
The ILP search took 12,975 seconds.
Wow. Okay, so that's more than 3.5 hours just to optimize one small section of one chip design.
And that's if nothing changes. In the real world, you iterate. You change one little thing, run it again, find a new problem, run it again.
So as an engineer, you'd make a change and then go get coffee for 4 hours to see if it worked.
Exactly. It was a fundamental constraint on design complexity itself.
That makes sense. It was a log jam. So the goal wasn't just to make the brute force search faster. It was to completely change the problem, to transform that tangled mess into something structured.
They needed to find a loophole in the math.
And this is where the genius of the new approach really shines. The breakthrough wasn't a faster computer chip, it was a mathematical insight.
A realization that the entire system of constraints could be modeled really efficiently as a network flow problem.
But there was a key condition, right? It only worked if they fixed one thing first. The left-right merge ordering. The LRM. That is the absolute key. The moment you fix that, the intractable problem becomes tractable. For any two cuts, they have to have a fixed relationship. One is left of the other, one is right of, or they merge. Once you decide on that relationship for every pair,
Even if it's just a guess at first.
even if it's a guess, you collapse that infinite search space of ILP into something a computer can solve fast.
Okay, let's walk through that transformation.
Yeah.
Take the physical layout, you fix the LRM ordering, and you turn it into a standard graph problem. What does that look like?
You build a directed graph. Every single cut, $Dollars on your chip, that becomes a node. $5 in your graph.
A little dot.
The little dot. And every physical rule, every spacing requirement becomes a weighted edge connecting two of those nodes.
Hold on, so an edge represents a rule. What does that mean?
It's an inequality, a simple one. If you have the coordinates of two cuts, 6 and 6JJ, the edge just represents a rule like 6J leaks Cij. It just means the distance between cut I and cut J can't be more than some amount.
That is brilliant. You're taking messy physical space and turning it into clean algebra that a computer can just chew through.
As long as that LRM is fixed. And we model 4 main types of constraints this way. First is separation, making sure cuts are at least a little ballers apart.
The minimum distance.
Right. Second is merging. This is critical. It makes sure that cuts that need to align vertically share the exact same coordinate. $6 equals XJ dollars.
Okay, what about the performance trade-off? The wire extensions.
That's the third type, extension constraints. These edges limit the maximum distance between the two cuts that define a wire. It keeps that signal drag, that capacitance in check.
And the fourth is just keeping everything on the chip, I assume.
Basically, yeah, bound constraints, making sure the cuts stay within their allowed gaps.
So by mapping this all onto a graph, you're looking for the best possible positions for all the nodes that satisfy all the edges, while minimizing the total cost. What is the cost here?
The cost is framed as the dual of a min-cost flow problem. The flow in this network sort of represents the movement of the cuts, and the cost is the two things we care about: the number of spacing violations and the total wire extension penalty.
I have to stop you on min-cost flow. For someone listening, how should they visualize that?
Yeah.
Why is it so much faster?
Okay, think of it like a plumbing system. You're trying to push water, that's the flow, through all these pipes. The pipes are your constraints.
So each pipe has a capacity, a maximum distance allowed.
Exactly. And each pipe has a cost to use it. That's the wire extension penalty. The algorithm just finds the absolute cheapest way to position everything without any pipes overflowing. And that kind of problem, unlike the ILP search, can be solved optimally and incredibly fast. It breaks the back of that exponential bottleneck.
So just switching from ILP to network flow is this huge mathematical leap. But the engineers didn't stop there. They added a really clever move that the old brute force methods just didn't consider.
Yeah, this part is really cool. Conflict removal via cut insertion.
Which sounds completely backwards. You solve a problem of too many cuts being too close by, adding another cut.
I know it's counterintuitive,
Yeah.
but it's an innovation that recognizes that sometimes you just can't fix a conflict by sliding cuts around. The layout is too dense.
So how does adding a cut help?
It creates a bridge. Imagine you have two conflicting cuts, $2 and those $1, on adjacent lines. The new strategy is to strategically insert a new cut, $2, on the line right between them.
Okay.
And if you can place that new cut, $2, so that it can merge with both of the original cuts.
You combine all three into one single larger feature.
Exactly. The original separation conflict just vanishes. Instead of trying to push two things apart, you just merge them into one bigger legal thing. It's a very elegant way out of the problem.
And that avoids having to use more extreme measures later on.
It significantly reduces the number of conflicts that would otherwise have to be flagged for, super expensive and slow techniques like E-beam lithography as a last resort.
So let's put it all together. They built this iterative framework using all these new tools. What's the flow?
It starts with that crucial first step, LRM determination. And they actually run it multiple times with a randomized start to explore different orderings.
To find the best initial guess.
Right. Then they run cut redistribution, pass one. That's the main min-cost flow solver, giving them the first optimal positions.
Then it goes hunting for the really tough conflicts that are left over.
And it uses that clever conflict removal via cut insertion snap on them. After adding the new cuts, it runs a final cut redistribution pass two to just clean everything up and refine the new positions.
And only if there are still conflicts after all of that do they get flagged for the expensive stuff.
Exactly. It's an automated, multi-stage attack on the problem.
Okay, let's get to the payoff. The results. This didn't just save a little time. This was the 200x performance leap. Give us the numbers.
So the average CPU time for the old ILP method across all their tests was 1,662.5 seconds. The new network flow method, 8.69 seconds.
8. That's
Yeah.
almost nothing. It's nearly instantaneous.
But the real world test is that massive 8,000 line layout, the one that took over 3.5 hours before.
What did it come down to?
From 12,975 seconds down to just 65.88 seconds.
So just over a minute.
Just over a minute.
That changes everything. You go from an overnight process to something you can do at a coffee break.
And what's more, the quality of the solution was just as good, often better. It usually had a lower total cost, meaning less wire extension, better performance.
And I saw it even reduce the need for those follow-up manufacturing steps.
It did. It needed about 7% fewer of those expensive E-beam cuts than the ILP method. And that's a direct result of that clever cut insertion strategy solving problems earlier in the process. It's a tangible cost saving.
So ultimately, this isn't just about a faster algorithm. It's about redefining what's even computationally possible at the very frontier of technology.
It is. By taking this critical optimization step from hours down to minutes, this framework becomes a key enabling technology for future chips.
And this has direct, real-world impacts for you, the person listening. Faster optimization means faster design cycles for engineers. They can iterate more, they can design better, more stable products.
It also allows for greater design complexity. They can now tackle bigger, more powerful chip designs that were just computationally infeasible before this.
And most critically, it helps clear the path for Moore's Law to continue. It ensures that as we go to sub-10 nanometer nodes, we can actually design layouts that are efficient and manufacturable.
It's fundamental to continuing the progress that we all depend on.
So we've learned how fixing one key thing, that LRM ordering, suddenly made the whole impossible problem solvable. But remember that very first step, the LRM determination. The paper mentions it starts with a randomized selection, and they run the whole thing multiple times to find the best result. And that raises a fascinating final thought for you. In these incredibly complex, chaotic systems where the number of possibilities is nearly infinite, is introducing a little bit of controlled randomness at the very start of a deterministic process, sometimes the most powerful and maybe the most elegant way to reliably find that one single optimal solution. Something to think about.